Okay, in part 2 of our series on groundwater sustainability, we are going to continue our discussion and look at what I'm calling equilibrium dynamics. So our objectives here are to understand how something called equilibrium and capture relate to groundwater sustainability. After we get through this video, you should be able to define these terms transitional storage and groundwater mining, and finally be able to define the water budget myth and the impacts it has on groundwater management policy. And so I kind of referred to this in the previous video, saying the aquifer dynamics can make assessing sustainability a little complicated. So let's talk about that. First of all, let's imagine excuse me, that this is a natural groundwater system. And what I mean by that is it's the state of an aquifer prior to any human interaction. So there are no wells, no groundwater withdrawals from wells. And before humans came along and started drilling wells, all aquifers were in this state of quasi-equilibrium. And what that means is we have input to the aquifer through precipitation and recharge. Sometimes there's input through losing streams or lakes percolating down to the aquifer. And then water is lost through transpiration, evaporation, and discharge to springs and streams. And over time, this reaches a state of equilibrium where the higher the water table gets, the more water is discharged. So let me back up a little bit. Let's suppose you have an increase in recharge. Maybe you're going through a wet cycle. That would cause the water table to go up. And when the water table goes up, it's going to discharge more water to a stream or to plants through transpiration or evaporation. And over time, it reaches a new state of equilibrium. And if we go through a long dry period, then the water table drops, there's less discharge, there's less evapotranspiration. Again, it reaches a state of equilibrium. And so this is just a written summary of that. In natural systems, the inflows to the system are shown on the left. You have aerial recharge from precipitation that percolates down to the water table. And then it says recharge from losing streams, lakes, and wetlands. So we don't, up to this point in our video, we don't normally call this recharge, but it is a form of recharge. Basically, water percolating down or coming into the aquifer from losing streams and lakes. The outflow would then be discharged to streams, lakes, wetlands, saltwater bodies, springs, or lost to groundwater evapotranspiration. And so, again, your inflows in whatever combination have to balance your outflows to be in a state of equilibrium. Okay, now what happens when we start pumping? So this quote is a famous quote from one of the pioneers of groundwater analysis and modeling named Tice, and he wrote a landmark paper in 1940. And it says, under natural conditions previous to development by wells, aquifers are in a state of approximate dynamic equilibrium. So this is what we just talked about. We call it dynamic equilibrium because it's not perfectly steady state, but there are some ebbs and flows, but overall it's in a state of equilibrium. Discharge by wells is thus a new discharge superimposed on a previously stable system, and it must be balanced by an increase in the recharge of the aquifer or by a decrease in the old natural discharge or by a loss of storage in the aquifer or a combination of these. So, using a diagram, this is a natural groundwater system, and it is in a state of equilibrium where the discharge is equal to the recharge. Then, if we add pumpage, we create an imbalance. And in the very short term, that imbalance, that just means we have more water coming out of the aquifer than is coming in. And so what happens in response to that? So let me back up a little bit. So this on the left, it says there's an increase in recharge. When you start pumping, that draws the water table down. When you draw the water table down, that causes maybe a gaining stream to become a losing stream, or it loses more water to the aquifer. So that results in an increase in recharge. Or there could be some locations where the water table meets the ground surface and the ground is saturated. If the ground is saturated and it rains, it can't percolate into the aquifer. So we call this rejected recharge. But if we lower the water table and that ground becomes dry, then we can actually get more recharge. So that's what it means by an increase in recharge. Furthermore, as you pump and the water table drops, you could get a decrease in discharge. So maybe less water goes to evapotranspiration, less water is discharged to a stream, and so forth. And overall, the water we need to pull out of our pumps comes from increased recharge plus decreased recharge plus this item in the middle, water removed from storage. And so that's shown in the middle of the blue diagram in part B. We can just start removing water from what's stored in the aquifer. And so as pumping begins, we have increased recharge, water removed from storage, and decreased discharge. Eventually, as the water table drops far enough, we're going to reach a point where we have a new state of equilibrium. And in the new state of equilibrium, the amount you need to pump out of the ground is balanced by some combination of increased recharge and decreased discharge. And now that can take some time to go from the old equilibrium to the new equilibrium. And in that process, in order to reach that new equilibrium, we have to lower the water table. And so there's some amount, no matter what the circumstances may be, we're going to end up removing some water permanently from storage as we do this. And this is called transitional storage. The water lost from storage as a system evolves from one equilibrium state to another. So to help you understand this, I've got a series of diagrams from the USGS paper book on this. So let's suppose that we have this simple system here where we have water coming in through recharge and it's being lost to a stream. And the discharge to the stream perfectly balances with the recharge. Now, we're going to go in and at some distance from the stream, we're going to put in a well and start pumping. As we start pumping, what happens is we're going to be removing some water from storage. So as the cone of depression develops here, that water that previously was up here in this part of the aquifer is now lost. That's where our transitional storage occurs. And whereas previously all of the water was going to the stream, now much of the recharge is going to the well. So there's a decrease in the amount of water going to the stream. And over time, you may get to the point where this stream switches from a gaining stream to a losing stream. So in order to get enough water to pump out, we have to take the recharge that's coming in, supplement that with discharge from the stream, and that eventually would reach a new state of equilibrium. So this, again, we had an equilibrium before we pumped, then we go through this transitional phase, and then eventually, if the water table gets low enough, we reach a new state of equilibrium where everything is balanced. And this is a diagram. As we pump over time, the percent of groundwater pumpage. So initially, when we start pumping, 100% of the water going out of the pump comes from storage. But then over time, as this water table drops, this flow direction with the stream will gradually be reversed. And over time, a higher and higher percentage of that water going to the pump comes from stream flow capture and less from storage. And so we reach a new state of equilibrium. Now, by the way, there are cases where you never reach a new state of equilibrium, or it happens over centuries or thousands of years, which is effectively never. And if equilibrium is never achieved and the water table just keeps dropping slowly over decades and centuries, the aquifer is said to be in a state of groundwater mining. Perpetual groundwater mining is a term that's used. And this is just another term associated with unsustainable groundwater use and groundwater management. Now, there are a number of aquifers. There are aquifers all over the world that are in a state of groundwater mining. One of the more famous ones in the United States is the Ogallala Aquifer, which is in the central U.S. and Kansas and Colorado and panhandle of Texas. Most of the water in the Ogallala Aquifer is glacial meltwater, and for years it's been overpumped and in a perpetual state of groundwater mining. In many parts of the western United States, groundwater mining is outlawed as a matter of policy. Or I shouldn't say outlawed. It's not allowed as a matter of policy. So if you apply for a groundwater pumping permit in an aquifer that's already fully taxed, it will be denied. And the state of Utah, as we have some aquifers here, as I showed you on the previous slide, that are being overpumped, but they're gradually working to a state by managing the groundwater withdrawal permits to get that back to a state of equilibrium. And the state of California has the Groundwater Management Act, which was passed 10, 15 years ago, that required that all aquifers in the state of California, that the management plans be updated and managed such that we don't have the problem we had, say, in the San Joaquin Valley. And that's been a big success so far. Okay, so what does all this have to do with groundwater modeling? The best tool to assess groundwater sustainability and how long it takes to get equilibrium based on management strategy, pumping rates, well field development. The best way to analyze that is through groundwater modeling. And so this is a hypothetical case that was originally developed by a famous groundwater researcher named Bredehoft. It's been reproduced in some other papers on the topic of sustainability. And he set up this hypothetical aquifer that's 80 kilometers by 40 kilometers. It's fed on the west side by a pair of streams which provide recharge into the aquifer, the primary recharge. The assumption here is there's little normal recharge from precipitation. It's primarily from the streams. And before pumping occurs, this groundwater basin fills with water, and on the east side, on the right, the water table is shallow such that there are a number of phreatophytes. Now, a phreatophyte is a plant where the roots go down into the aquifer And so there's a substantial amount of evapotranspiration that occurs in this area. And so the theory here is that prior to pumping, the recharge from the streams is perfectly balanced by the water lost to the phreatophytes through evapotranspiration. And then if you put in some wells, now the way the model was set up, there are two cases. Case 1, the wells are over here in the middle of the valley. Case 2, they're over here right next to the phreatophytes. And in either case, shortly after pumping, the pumping is balanced by decreased discharge. So as the water table drops, the amount of water available for phreatophytes goes down, and the phreatophytes start drying off, and that leads to a reduction in discharge to the phreatophytes. But there's also water pulled from storage. The only way the water table will drop is if you're pulling water out of storage. So eventually, if the water table drops enough, then 100% of this discharge to phreatophytes could be canceled or eliminated, therefore achieving a new equilibrium. And just for the sake of argument, the quantities have been set up to where prior to pumping, the discharge to the phreatophytes is perfectly balanced by the recharge, but the pumping rate for these well fields is exactly the same amount as the discharge or the recharge. So there's a balance. And so if you're taking my class, we have an exercise for your homework where I build a version of this model, and you're going to be able to run this yourself. But interestingly, what you can model with a computer model is how long it takes for that water table to drop based on the hydraulic conductivity and the geometry and shape of the aquifer, how long it takes for this to come to a new equilibrium where you lower the water table enough to completely cease the discharge to the phreatophytes. And that is shown in this diagram here. So case 2 is the one that was closer to the aquifer. So let's look at case 1 to begin with. That's the one in the middle. And so the vertical axis is the discharge to the phreatophytes in units of cubic meters per second. It starts out around just about 2.8, 2.9, and then over time, that eventually comes down and becomes asymptotic. But what's really interesting here is case 1, which is right here in the middle of the basin. So, it's a number of kilometers away. It takes, you get up to 1,000 years and you're still not fully at equilibrium. There's still some water being lost to the phreatophytes, discharged phreatophytes. And case 2, now we put it right next to the phreatophytes. And in that case, it takes 100, 200, 300, 400, almost 500 years to get to full capture. And so now it would be interesting to rerun this case where the wells are right on top of the phreatophytes. I'm sure it would be faster, but it would still take a long time. So the takeaway from here is that going from one state of equilibrium to another can take a long time, and over that long period, you can pump massive amounts of water out of storage, water that's permanently lost to storage. And if you were to imagine a case where the wells are right over here, the only way you could eliminate the discharged phreatophytes would be to completely dewater the entire basin. And if you did that, I'm sure you would have problems with subsidence. You'd probably have a lot of subsidence and permanent loss of storage. And so the location of the wells is really critical in terms of your ability to reach a new state of equilibrium. And so this illustrates some really important principles. And let's summarize some of the takeaways here. If we go back to the Tice article in 1940, he identified this same problem. In fact, it was identified by researchers as early as like 1905. And Tice articulated this, saying the pump should be placed as close as economically possible to areas of rejected recharge or natural discharge where groundwater is being lost by evaporation or transpiration by non-productive vegetation. Meaning the location of the wells matters. In localities developing water from non-artesian aquifers and remote from areas of rejected recharge or natural discharge, that would be the phreatophytes in our example, the condition of equilibrium connoted by the concept of perennial safe yield may never be reached in the predictable future, and the water used may all be taken from storage. Another term for this is perpetual groundwater mining. And so, again, to reiterate, sustainable groundwater management is not just having a water balance. The location of your wells relative to the natural discharge points is critically important. And this leads to a term which was coined by Bredehoft and some other researchers in 1982 called the water budget myth. And it's perhaps the most common misconception in groundwater hydrology is that a water budget of an area determines the magnitude of possible groundwater development. And I can tell you that the reason that we have a lot of aquifers, especially in the western United States, that are not being managed sustainably, where our groundwater levels are continuously decreasing, is because at some point someone decided that let's just estimate the amount of recharge we have and then allocate groundwater withdrawal permits equal to that balance. Assuming that that's all you need is that balance on paper. The ultimate production of groundwater depends on how much the rate of recharge and or discharge can be changed, or how much water can be captured. When we say captured, we mean water that's being discharged to springs or streams can be captured by lowering the water table due to pumping. Although the knowledge of the virgin rates of recharge and discharge is interesting, such knowledge is almost irrelevant in determining the sustained yield of a particular reservoir. Somehow we've lost or misplaced the ideas that Tice stated in 1940, so he's referring back to the previous slide. So, what are some of the takeaways here? We learned about transitional storage and going when you add a new stress, new wells, you transition from the original equilibrium state to a new equilibrium state. And in so doing, to get it to a new equilibrium state, you have to lower the water table and remove water from storage. That's called transitional storage. Ideally, you eventually reach a new state of equilibrium. But if your wells are located at a point that's too distant from the natural discharge zones, you could end up with perpetual groundwater mining where you never reach a state of equilibrium. And so these are the main important principles of sustainable groundwater management. And again, groundwater models can be a really valuable tool in simulating the groundwater dynamics, whether or not discharge points can be captured, how long it takes to reach a new equilibrium, etc. So those are the main points on groundwater sustainability and aquifer dynamics related to sustainability. Thank you.